record. It's okay. Next time can someone remind me? I mean, one of you who can remind me to record, okay?
Okay.
Okay. All right. Okay, for negative cycle. Okay. All right. So for negative cycle, this is what it look like. So in negative cycle, I will use green color. So in this case, okay, I think I want to delete the red one. Oh no, is it complicated? We can complicate it. No, I don't think so. So this will be negative, this will be plus, okay? The top one negative, the bottom one plus, okay? In this case, okay, the direction, remember your current is in from negative to plus, so in this direction. Therefore, you will have D1 on, okay, and then meet your power supply, okay, and then go to this direction to your D4, and to V out, okay, in this direction. So in this case, D1 and D4, D1 and D4 is forward bias, and D2 and D3 now reverse bias. Okay, done. Okay, so if you draw the equivalent circuit, will be similar as this one. Okay, so if it is similar, so you draw the equivalent circuit. Okay, if you draw your equivalent circuit, so you will get okay. So if you draw your equivalent circuit, you will get minus V secondary. It will be looks like this. Okay, let me recall back in the previous slide. The previous lecture. So this is how it looks for the negative cycle. So negative plus, and then you have this. Why this D3 and D4? Because of the notation of the diode. Okay, don't get confused with that. Okay, all right. So let's draw the equivalent circuit. So you have negative on top, positive below. So you have negative and then positive V secondary. Okay, and then you have negative V secondary connected to negative D1. Okay, and then positive D1 to the ground later, and then positive V secondary there connected to positive D4. Okay, so positive D4. All right, so negative D4 connected to positive RL to the V out. Okay, so this is kinda terbalik sedikit lah. Okay, so you have ground over here. So this is plus minus V out. All right, so let's do KVL. So it will looks like this lah, the KVL. So your KVL will be same, okay, negative V secondary peak plus 0.7 plus V out peak. Okay, plus 0.7 equal to 0. Okay, and then you will get your V out peak the same value, okay, which is 55.17 volt. Right, okay. Let me write properly here. All right, so this is the value. Okay, this is the value. Okay, done. Okay, for this one, is it done yet or not done? Is it done?
Not not done.
Yes, not done. What's next? We are still
No.
at A. What's next? No. What's next for
The
part
wave
one?
wavefront.
Yes, the waveform. Okay, the waveform. Okay, not finished yet. You need to draw the waveform. Okay, so the waveform will be, so this is V out peak. Okay, and then you have a full wave waveform, definitely like this. Okay, you can draw how many cycle you like, but then put labeling here. So this is 55.17. All right, that's it. Done for part A. Okay, not for part A, for part 1. Okay, so this is solution for part 1. Okay, now let's do the solution for part 2. Okay, part 2. Wait, okay, all right. So for part 2, okay, can you give a second? It's kind of delay here. Okay, for part 2, calculate the average and as well as the peak inverse voltage. Okay, I need to have another slide here. Okay. Okay, so for part 2, oh, okay. Part 2, V average. So what is V average? It is VDC. What is the formula here for VDC?
2V peak over pi.
All right, correct. So 2 V out peak over pi. V out peak, okay? Remember, so 2 times 55.17 over pi. How much? Student? Hello?
35.
All right, 35.12.
35.12.
0.12.
All right, volt. Okay, get the answer. Now, number 3 is determining the peak inverse voltage at D1. Okay, look at the formula again. Okay, peak inverse voltage is equal to too much at the back at the 1. Okay, so it is equal to
V peak
yes, V out peak.
plus 0.7.
Okay, plus 0.7. Okay, so it will be like 55.17 plus 0.17. How much? 55 lagi ke?
55.87.
55.87 volt. All right, great. Okay, done. Okay, done. So you've done for at least 7 marks. In the previous lecture, the load line covers you about 7 to 8 marks. Okay, as well as the PN junction theory about 3 to 4 marks. Okay, you covered that. Okay, if you do the tutorial given by me, okay, you have covered some of the PN junction from test question, and you also have covered the DC load line from the test question, and now the power supply for full wave rectifier you have covered as well. Okay, no matter what type of configuration out during the test, at least you know how to solve for both. Okay, they won't ask you both. Okay, not like center tap and bridge ask at the same time. No. Okay, they will ask you either one. Okay, make sure you know how to do it for both. Okay, at least today we have done for the bridge network. So this is the past answer which I have shown you in my own way, but I also have uploaded the solution here. Okay, so this is a summary. Okay, from this summary, the center type, wait, I need to find my cursor. Where is my cursor? Okay, so for the center type, the output waveform, of course, a full wave rectifier, they will be the same. Okay, for the V out, so this is the formula. Okay, but then I don't want you to memorize the VP out formula and so on. You need to understand, okay, how to do the KVL and so on. But you need to know that, of course, okay, for the V to convert between RMS to peak, you need to know the formula, and also for the PIV. Okay. Okay, next is filter. Okay, so we have done the rectifier part, settle. Okay, at least you have got your output now from the sinusoidal like this. Now at least you have the positive, the full wave signal. Okay, you are able to get this after the rectifier. Okay, next is you have filter. Okay, filter. So what is the function for filter? So filter, it is used to eliminate the fluctuation in the rectified voltage and to produce a relatively small DC voltage. Okay, so the objective, students, okay, after this full wave rectified output signal, okay, and then you go to filter circuit. Okay, the output for filter circuit might get this kind of waveform, okay, with a little bit ripple, where we call this there is a little bit ripple here. Okay, not as smooth straight line yet, but almost there, but with a little bit ripple. Okay, so you have a full wave signal, sinusoidal like this, and then you have rectifier, no matter what type of rectifier. Okay, you got the output like a full wave waveform like this. Okay, and then you go after full wave waveform. So this is your full wave waveform. Here is full wave waveform. Okay, now you have a filter circuit. So the output for filter circuit has a ripple there. Okay, so how does it looks like for the filter circuit? So this is how it looks like. Okay, so you have, of course, you have your transformer. So means that your question here will be bring forward to the filter. Okay, you have done up to this part. You have done, okay, to find the waveform. Okay, which is like this. Okay, the waveform. Now the circuit is next is connected to the filter, which is capacitor, and also you have RL. Okay, RL resistor. Okay, so filter in a power supply is capacitor. Okay, it is to reduce the variation of the output voltage from a rectifier. And the remaining voltage variation, okay, this one, we call it as a ripple. Okay, ripple. So generally, the ripple is undesirable. Okay, we don't want that. Okay, the smaller the ripple, the better. Okay, means that the smaller the ripple, you will get like almost a straight line. Okay, as you can see here. Okay, as you can see, the one that a very light color here, that is your full wave signal. Okay, and then after it go through a filter or capacitor, it will start to, okay, here means that it is store charge. Okay, during this ripple, it is actually discharging and then store charge again and then discharging. So this is how it works actually, okay, to convert between a full wave rectifier to almost straight line DC voltage. So how they do, they use it as a filter to charge and discharge the storage, okay, the charge, okay, in order to get a straight line output voltage. Right. So this is how, okay, half wave is not covered in your syllabus. Okay, this is not covered in your syllabus. So only full wave. So as you can see, okay, during the period of in between cycle, in between output here. So this is your output. Okay, the first one in between the cycle, there is a discharging. Okay, and then starts charge again, and then discharging. Okay, so that is how it works. Okay, for the filter. Okay, basically filter is to reduce the variation in the rectified circuit voltage. Okay, filter is simply a capacitor connected from the rectifier output to ground, and a small amount of fluctuation in the filter output voltage, we call it as a ripple. Okay, ripple, and we are actually can calculate this ripple factor. Okay, it is an indication of the effectiveness of the filter. The less the ripple factor, the better. Okay, means that less ripple means this discharging took faster time. Okay, if it's the ripple less, it is more closely looks like a straight line. Okay, a straight line like in this figure, most likely closely like a straight line. So we want that. Okay, why half wave filter not covered? Because it take longer time to discharge. Okay, for full wave it takes smaller time to discharge, but then when your ripple factor smaller means it take this much smaller time to discharge. All right. So this is how it looks like. Okay, so this is your waveform. Okay, initially your waveform is it is actually like this. So you have, do I, okay, so actually initially you have like this. Okay, oops, is it like this? At my drawing. Okay, so this is the discharging period. Okay, so initially the full wave looks like that. Okay, so the ripple factor is an indication of the effectiveness of the filter. Okay, so to calculate the V ripple factor, okay, so this is the formula: V ripple peak to peak. Okay, peak to peak means that from this point, okay, to this point. Okay, to this point. So this is how you calculate the V ripple factor. V ripple peak to peak is equal to V peak over 2 FRL and value capacitor. So this V peak is represent to your V peak out. Okay, the one that you have calculated after the rectifier just now. So now to find the V ripple peak to peak by using this formula. Okay, this formula. It is equal to the V peak out over 2 frequency you have, resistor RL also you have, and capacitor value will be given. Okay, so the RMS is given by this, the same equation. If give you like a reverse question, give V ripple in RMS, then you have to convert it in V ripple peak to peak over 2/3. Okay, and then after that you have a VDC. Okay, VDC equal to V peak out minus half V ripple peak to peak. Okay, so this is the ripple. So this is ripple. Okay. All right. So V ripple peak to peak is from this point to this point, which is equal to the V ripple peak to peak. Okay. Where does the VC, okay, VDC is actually in between this ripple. Okay. When V ripple divide by 2, so as you can see, VDC from V ripple divide by 2 to 0. So this is your VDC. Okay, to calculate your VDC, therefore you have at this point is your V peak out. If you still remember from the past, okay, this point is V peak out. Okay, to calculate your VDC, for example, usually V ripple peak to peak is given. Therefore, VDC here is equal to V peak out. So So I will put this V peak out minus half V ripple peak to peak. So you will get this. So it is actually the same value if you use 2V peak out over pi. Okay, we will see some kind of this kind of question where we have a capacitor there. Okay, so ripple factor given by this formula, which is R equal to 1 over 4 SEEE1073 FRL capacitor value. Okay, so this is a summary for the filter. Okay, so I didn't put the example for the capacitor. Okay, I will put the example in your next tutorial. Okay, all right. So, however, I hope that you understand, okay, what is filter all about, okay, what is the output of the filter. So it has some sort of a ripple, so you have to draw it with the ripple there, and you have to know the parameter when you have output filter. The parameter involved here is V ripple peak to peak, okay, V ripple peak to peak, okay, and then from this V ripple peak to peak, where is actually your VDC? It is actually from half of V ripple peak to peak to the zero. Of course, at this maximum peak point here, this is your V peak output. Okay, this is a summary. All right, so let me continue on the last part, which is voltage regulator. Okay, for the voltage regulator, consists of what? Okay, so you are almost there. So this is your input signal, sinusoidal waveform, and then you have rectifier, okay, with a full wave rectified signal, and then you have filter. You have almost straight line, but with a ripple where you can find the ripple voltage. Finally, you have a voltage regulator, which is usually in the form of Zener diode. Okay, Zener diode. Okay, so after this voltage regulator, where it used to regulate or to maintain the constant DC voltage for variation in input line voltage or in the load. Okay, so usually after the regulator, you will get a straight line DC output voltage, straight line DC output voltage like this. Okay. Okay, so Zener diode is used as a voltage regulator because Zener diode can act as a regulator when it is on state. Okay, like I said in the chapter 2, part 2, okay, Zener diode is different with normal diode because it is fabricated with a heavily doped and different material, so it tend to have a very high voltage, okay, very high voltage, and sometimes greater than 10 volt. Okay, usually power supply we have a high voltage. Okay, for example, you want your output voltage, okay, from here is 240 volt RMS input. Okay, your objective to get a 10 volt DC power supply, a constant 10 volt DC power supply. So you use a voltage regulator. No matter how much you get your V peak out here, but when this voltage regulator regulate, okay, it will be a constant voltage of 10 volt, for example. Okay. Okay, so it maintains nearly constant voltage. Okay, so how it is looks like, okay, across the terminal, like I said, Zener diode in the previous class, it's a very different with the normal diode. If you have normal diode, this part is positive, the other side is negative, but in order to connect your Zener diode correctly, it is connected like this, okay, in such a way where this part is positive, the bottom part is negative. This vice versa to the normal diode. Okay, I think you all know. Okay. All right, so resistor, of course, you have RL, okay? So RS is to limit the Zener current. So this RS is to limit the Zener current so that it is less than the maximum current IZM, okay? We know that in Zener diode, where it works, where it behaves in reverse breakdown voltage. Okay, so it has its own maximum Zener voltage. Okay, we don't want to reach this maximum Zener voltage because your circuit might be broken. Okay, we don't want that. Therefore, we put a RMS. We put a RS to limit the current of this IZM. Okay, we know that inside here internally it has Isaac M. Okay, but then we use resistor to limit the current. Okay, so that we only we didn't get the maximum. Okay, we limit the current. Okay. All right. So other than that, okay, how to determine the Zener act as a regulator or not? Okay, we don't know. Like I said just now, same like normal diode. Normal diode could be forward bias and it is on. For reverse bias, it will be off. Okay, for Zener diode, it could be two. It's either it is regulate or not regulate. Okay. But how do we define whether it is regulate or not regulate? There is a step to do it. Okay, there is a step to do it. How? For example, this is your given circuit. Okay, given circuit is this one, student. Okay, where you have the any input signal. So if you can imagine that, so whatever input here, if this is a continuation, okay, this is a continuation. Okay, now we are looking the circuit at here, okay, in between the voltage regulator. So we know that the everything going inside this voltage regulator is the V out here. Okay, is actually the value that you have calculated, the V peak out here. See the V peak out here. So, or also the VDC. It is actually the VDC. Okay, so this is, for example, from the past of your circuit here, where you have rectifier, and then you have filter, and then now you have your regulator circuit. Okay, this is your regulator circuit. All right. So this input would be your VDC, okay, from the past circuit that you have calculated. Okay. So this is how it looks like. Okay. It has RS, okay, to limit the current, and you have regulator, VZ, and finally RL. Okay. To define whether this Zener diode regulate or not, okay, you need to use Thevenin theorem. Okay, Thevenin theorem. This theorem. Thevenin theorem usually a voltage divider theorem lah. I think I have shown you some example during DC load line. Okay. Okay, this is how the circuit look like. Okay. But because this 2 point is parallel, I switch the circuit, okay, so that it looks like a Thevenin circuit where we bring RL to the front and VZ to the back. Is it okay? Yes, it is okay because it is in parallel. Doesn't matter if you switch the place, okay? Why this is being switched the place? Because I want you to see clearly, okay, how V Thevenin is solved, okay? So now you are solving this Thevenin part. Okay, this Thevenin part. Okay, so V Thevenin here is equal to anyone? V Thevenin? V Thevenin across from here. Therefore, it is a voltage divider. We are taking this RL over RL plus RS times VS. Okay, and then you will get the R Thevenin. Okay, R Thevenin, where you short this VS, you will get RL parallel with RS equals to this value. Okay, now you are getting this V Thevenin. Now you get your value VThevenin here. Okay, how to define your whether the Zener diode is regulate or not? Okay, if you redraw again the circuit, you will get your VThevenin and RThevenin, and this is your VZ. You're not finished yet. Okay, how to define whether it is regulated or not? Okay, in this VZ, okay, usually it will be given the value for the Zener voltage. Okay, for example, in this question, given Zener voltage 10 volt, okay, determine whether the Zener voltage regulate or not. Okay, from your calculation of VTH just now, if your VTH value less than the VZ given in this Zener diode, means that your Zener diode doesn't regulate. Okay, means that regulation does not happen during that time. If your calculation of VTH is greater or equal than the VZ given, therefore your Zener diode function as regulator. Means that your Zener diode regulated. Okay, I will show you the example. Okay, VTH or Thevenin at least must same or equal than the VZ. Okay, in order for the Zener diode to be regulated. All right. So this is a summary. Okay, so this is same IV characteristic that have been shown in the past class. Okay, so this is the normal diode and this is for the Zener diode. Okay. Okay, let's take a look on the example. Okay, so this is the example for the Zener diode. Okay, now, given this circuit, like I said, so given this kind of circuit, so this is actually your VS just now, and this is your RS, and this is your Zener diode, and this is your resistor. If we redraw again the circuit, student, you might see, okay, let me rearrange a little bit here. Okay. 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 If I rearrange it, I will get something like this. So we have plus minus 20 volt. Okay. And then you have RS here, which is 100 ohm. Okay. Now I draw the RL in front. Okay. Draw this. Okay. So this is 150, and then you have your VZ. Yeah, so I just draw it like this. Okay, so for example, in this case, given the VZ 10 volt, okay, you might have to solve the Thevenin part here. Okay, the Thevenin part. So V Thevenin here is equals to 150 over 250 times 20. Okay, you get the VTH value here about 12 volt. Okay, 12 volt. Okay, RTH is this one, parallel. Okay, now you want to define whether it is regulated or not. Okay, this 12 volt, okay, here is greater or less than the VZ given. Greater, right? So it is much greater than the VZ 10 volt. Okay, therefore, this Zener diode is regulated. Okay, Zener diode regulated. Okay, means that it works as a voltage regulator. Okay, right. So that's how you define it. Okay, it could be your VTH 10 volt. Okay, what happened if VTH 10 volt? Is it regulated or not?
Yes. Yes, regulated.
Yes, yes. What happened if the VTH less than 10 volt?
No
Sinar.
regulated.
Okay, it will not be regulated. Okay, so finally, so this is the actually Zener diode is sometimes used as an IC regulator. It looks like an IC. Okay, later I'll show you in the multi-sim. We will do multi-sim a little bit after this. Okay. And so this is some of example for voltage regulator IC. So there are many types. Okay, different types has different output voltage. For example, just now the voltage is 10 volt. If there is no 10 volt here, but if let's say the voltage of the Zener diode is 12 volt, then the type of number voltage regulator is 7812. right? Okay, so Zener diode as resistor load circuit. Okay, I think we have passed 1 hour or not? 5 more minutes. Okay, so Zener as a resistor load circuit. Okay, so the basic function of Zener diode is to maintain specified voltage. So for example, given this type of Zener diode, okay, and then to calculate whether it is regulated or not, I think you all know. In this case, the output voltage, if let's say the output voltage is regulated, means that the V out is 10 volt. For this particular example of Zener diode, the V out, this Zener diode is 10 volt. Therefore, the output here also 10 volt. Why? Because it is in parallel. Okay, parallel. So whatever voltage regulated here, that will be your output voltage of your power supply. Okay. Okay, as load resistor gets larger, okay, the load current IL decreases. Okay, more current burning through the Zener and putting the diode deeper into breakdown. Okay, as the load resistor gets smaller, okay, the load current IL, okay, drawing more current away, and this will cause less current through the Zener diode and bring it closer to the knees of the IV characteristic. Okay. All right. So how do we determine that? So there is a little bit what we call as circuit analysis. Okay. We will continue after this. Okay. Let's take a 5 minute break. Is that okay?
Yes, doctor.
All right. Okay. Have you all installed your multisim?
Yes.
All right. Okay. So we will do it today a little bit hands-on on the simulator. Okay. So I'll be back after 5. Back. Can you hear me? Hello all.
Yes, Doctor.
All
I
right.
hear you.
Okay. So there's one question here. Alex asked if the polarity of Zener diode change, will it become open circuit? The means that it is upside down, right? I mean, the location is
Yes,
upside down.
yes.
You mean? Yes, it will be open circuit. All right.
Okay, okay.
Okay.
Thank you.
Okay. All right. Okay. So can I continue? Just a little bit, few more slides. Okay. All right. Okay. So, right. Okay. Now, just now we have determined whether the Zener diode is regulated or not regulated. Okay. By doing that, you need to apply the Thevenin. Okay. Okay, next is other parameter involved. Okay, other parameter involved, for example, after you determine whether it is regulated or not regulated, okay, and then there will be a current flow to the circuit. Okay, along this RS, there will be IR. And then at Isaac, at Zener diode itself, it has Zener current, Isaac. And also at load resistor, it has IL. Okay, so now is to find all this current. Okay, the idea is actually, the idea how to solve it is actually by using KCL. Okay, means that total current, ayo, okay, total current in is equal to the total current out. Okay, in this case, what is current in to that particular node? What is current in?
IR.
Yes, IR. Okay, equals to what is current out in here? How many current out from that red node? Isaac plus IL. Okay. So this is KCL, okay? Total current in equal to total current out, okay? Whatever current in to this node is current in. Whatever the current out to that node is the total current out, okay? That's the tips, okay? So here are the steps actually. Okay, first step, so there will be only two steps, okay, to find all the currents. Okay, first step is find the voltage. Okay, means that it is what voltage is this actually? So this is a Thevenin. Okay, Thevenin just now where you have done this. Okay, if your V Thevenin, okay, VTH, okay, greater or equal, it will be on and blah blah blah. Okay, so for example, okay, for example, if it is on, okay, for example, if it is on, then the voltage drop across this diode, Zener diode, okay. If let's say you calculate, you get that, okay, you calculate, you get that this VZ is, sorry, V Thevenins or greater or equal, then you said the VZ is on. Okay, on means regulated. Okay, student, if that is regulated, so the voltage drop across this equivalent circuit will be equals to the, therefore, we take the VZ given. Okay, VZ given. All right. I'll show you the example after this. Okay. If let's say you calculate, you get that this is not regulated, means it is off. Okay. So you use V Thevenin calculated value. Okay. In your circuit here. Okay, I means you replace this value with VTH value that you have calculated here. Okay, remember that these two conditions. Okay. Okay, let's take a look the example one. Yeah. All right. So this is example one. Okay. First step, they said, first step is to determine whether the Zener diode regulated or not. Okay. So can all of you try to calculate how to determine whether it is regulated or not, student?
Find Thevenin first.
Yes, all right. Okay. Determine now. Okay. So Thevenin, you might have to draw the equivalent circuit. Okay, I'll give you time about 1 minute or 2 minutes. Hello? Hello? Can you all hear me?
Yes, betul.
Oh, okay.
Yes, yes.
Baru je boleh dengar. Tadi tak dengar.
Okay. Why you can't hear me just now? Because I didn't talk. I'm replying my message. Okay. All right. Sorry. Okay. Find VTH. Sorry. Yeah. Okay. Find VTH. So VTH is equals to, sorry. So 1.2K over 2.2K times 16 volt. Okay. Someone has calculated. Let me see the answer here in the chat box. 8.34. Sorry, 8.3. 8.73. Is it right? Did all
Yes.
of
I
you
got the
get
same
8?
answer.
Yes, great. Okay, so 8.73 volt. Okay, 8.73 volt. Okay, now look at the given voltage there. So it is less, okay, less than the VZ given. Okay, VZ given is 10 volt. So it is regulated or not regulated? So since VTH less than the VZ given, therefore this diode, this Zener diode not regulated. Okay, not regulated. Okay, done. Okay, now next, if it is not regulated, if we want to draw the equivalent circuit, how would it be? Hmm. All right, so the circuit will be so the VL here, okay, means that like I said here, okay, if it is not regulated, student, okay, if it is not regulated, means Zener diode off, we use the voltage across here, okay, is VTH that we have calculated, okay, which is in this case 8.73. Okay, if we redraw the equivalent circuit, okay, if we redraw the equivalent circuit, it will be like this. So this is VE 16 volt. Hello? Hello?
Yes, doktor.
Okay, all right.
Yes.
Okay. Sorry. Okay. Okay, so this is 1K. So voltage across here now, okay, become 8.73 volt. Means that since this is parallel, okay, since this is parallel, therefore this is 1.2K. So VL here is actually How much? How much is VL? Because that is parallel.
8.73.
Yes, correct. Okay, correct. So it is 8.73 volt. Okay, now you got your first one, VL 8.73 volt. Okay, next is VR. Okay, VR is voltage across here. VR. Okay, can you calculate VR now? What is your VR? How you find your VR?
16 minus X.7K.
Yes, correct. You apply KVL to the loop. Okay, so your VR, okay, apply KVL. Okay, so you will get like negative 16 plus VR plus VL equal to 0. Okay, in this case, VR equal to 16 minus 8.73, which is how much? How much? Hello?
7.27.
Okay, 7.27. Everyone get the same answer, 7.27?
Yes, Doctor.
All right, great. Okay, now we are settled. Okay, what happened to the IZ? That is the question now. Okay, since your Zener diode is not regulated, mean it is off. Okay, same like normal diode. If it is off, means your Zener diode open circuit, right? Yes, open circuit. So if it is open circuit, so if I can I padam this? Okay. If it is open circuit, so what will be your value for Isaac here? It is open. Therefore,
0.
0.
0, 0.
yes, 0. Okay. So therefore your Isaac is 0. Okay. Zener diode. Okay. Okay. Not regulate. Not regulated, therefore it is off, and open circuit, Isaac equal to 0. Okay, next is PZ. Okay, do you still remember P is equal to IV? Remember that? Still, right? Okay,
Yes, Doctor.
so if it is PZ, therefore Isaac VZ. Okay, so for this case, P is equal to Isaac and VZ. So Isaac is 0, therefore your PZ also 0 watt. Okay, so this is how you solve the question for the Zener diode. Okay, are you all clear? Clear? Yeah.
What
Yes.
is the use of PZM?
What?
What is the use of PZM?
PZM. Okay, so given in Zener diode, it will be given your both voltage. Okay, the Zener diode voltage as well as the maximum power Zener. Okay, but then this is no more regulated. Okay, it is already open circuit. Okay, so there will be no current flow and no power no power across the Zener diode. But if it is regulated, then we can use this value PZM, okay, in order to get the IZM, okay, by using this formula. For this particular case, we didn't use this value because it is not regulated. Okay, next example. We'll see we use or not. Okay, am I answering your question? All right. Okay. All right, next slide. Okay, so this is a solution, so you can look a proper solution lah. Okay, same one. Okay, now next example. Okay, first, okay, if the RL is 3k ohm, is used. All right. So now determine the VL, VR, and IZ. Okay. So first step. What is the first step, student? First thing first, you need to determine whether it is regulated or not. Okay. How? By using Thevenin. Can you do it now?
Yes, Doctor.
Can please all of you try. All right. So let's find the voltage V Thevenin. Okay, V Thevenin is equal to 3K over 4K. Oh my God. Okay, 4K times 16 volt. Okay, how much?
12 volt, Doctor.
All right, 12 volt. So I can see Alexei also 12 volt. Okay, Sabrina say also 12 volt. So means that all of you get 12 volt. Okay, so now it is greater than the VZ given. Okay, VZ given is 10 volt. Therefore, this Zener diode is regulated or not regulated?
Regulated.
Regulator.
Yes, regulated. Okay, it is on lah, basically. Okay, so we will take if we draw the equivalent circuit, okay, what value we will take what value?
10.
Yes, 10 volt. Yes, all right. So VZ equal to VL equals to 10 volt. Okay, this value given. Okay, 10 volt. So this is the first answer for the VL. Okay, why? Because it is parallel, therefore it has the same voltage drop here, which is 10 volt. All right, next, to determine your VR. Okay, so if I draw again the circuit, so it would looks like this. So I want to draw, although I have a very limited space here, so that you all can see what happened here. So this is 3K, this is VL, and this is VR, which is 1K and 16 volt. All right. Okay. So we know that this voltage is VZ 10 volt.
用不到
All right. Who's mom calling just now?
Ping An.
Sorry,
Your mom
sorry,
call.
sorry.
It's okay. Your mom calling you for breakfast? Okay, it's okay. Things happen. Okay, so now we apply KVL. Okay, apply KVL. So you will get here -16 plus VR plus VL is 10 volt equals to 0. Therefore, your VR is equal to 6 volt. Okay, you have done the VR part. Okay, settle this part. Okay, and then to get your IZ, okay, like I said, I said to you, okay, your IZ. So you know that, okay, since they use blue, so I use also blue. So we have here is IR, okay, in this direction. Okay, Isaac, of course, there, given there. And we also have here across RL is IL. Okay, so when I said apply KCL to this loop, I mean to this, the whole loop, means that total current in is equal to the total current out. Okay, still remember that during your ECA, student?
Okay, see. Yeah.
Yes, doctor.
KCL. Okay, total current in equal to total current out. Or total in the circuit, total current in the circuit equal to 0. Okay, so current in here, that's together. What's this?
IR.
Yes, IR equals to
Isaac. Yeah.
Isaac, yes, plus IL. Okay, now they want you to find your Isaac. Okay, first you need to find your IR. Okay, IR. Okay, let's rearrange here. So Isaac is equals to IR minus IL. Okay, now student. Okay, we do Ohm's law now. Okay, what is your IR here? How do you find your IR? By looking at your circuit, how you find your IR. What you already have now?
V of R.
Yes, correct. You already have the VR, right? So now you want to find your IR. So it is equal to VR over R.
R.
Yes. Now IL. Do you have the value for VL?
Yes, yes.
Yes, you do. Therefore, IL is equal to?
VL over RL.
Yes, VL over RL. So this is how you do it. So 6 over 1K minus 3K, 3K pula. VL is equals to, what is VL? 10, okay, over 3K. Can someone help me? How much is the Isaac?
2.66 I think it's almost 2 milliliter, 2 milliampere.
Again, one more time.
2.6 milliampere.
Again, one more time. 2 or 2.6. Okay. Thank you.
2.6
Okay.
milliampere.
All right. Thank you very much. 2.67 milliampere. All right. So I think all of you get the same one, can? Right? All right. So now you've done for Isaac. Okay. Next is PZ. Okay. We didn't use this PZM because the question asks you PZ, not PZ maximum. Sometimes the question asks you PZ maximum, whether you understand or not, you have to take the value from here. PZM equal to 30 milliwatt. Okay. But then they just ask you after regulated, they want PZ. So what is the value for PZ here? It is equal to the IZ times VZ. Okay. Okay, for this case, you are not using VZM. I mean the VZ. Sorry, not using the PZM. You're using IZ that you have calculated and also VZ that you have calculated from regulation just now. Therefore, it is equal to the 2.67 milli times 10 is equal to 26.7 milliwatt. Okay, so you've done the PZ and also IZ. All right. Any question? regarding this, student?
Doctor,
Yes.
when the Zener diode is not regulate, it will open circuit, right?
Not regulate.
Yes, will
Yeah,
if
it will
not
be open
regulate, open
circuit.
circuit. So
Yes.
if regulate, it will turn on. But why we didn't write the Zener diode in the circuit?
Oh, you mean here? You mean here?
Yeah.
Oh, okay. Yes, you can write. Oh, I didn't write just now because I don't want it to look complicated, because whatever value here you took, so this, oh, sorry. Yes, you can. Okay, so the circuit will be like this. So you have plus minus 10 volt, and this is 10 volt. Yes, the same one. Yes.
Oh,
Okay.
so tak penting pula doktor.
Yes, tak penting pun, sebabnya why not like tak penting. It's like okay, why I didn't draw it, because I want to make to find later the current, right? So I have to pass through this 10 volt, okay, in order for my loop to go through this 3k ohm. Because it's not like tak penting. It's not like this is not important. Okay, we know there is a voltage drop across here. What's your name?
Amin.
Amin. Okay, so we know that the across here we have voltage drop is 10 volt. Okay, and you know that this, I just want to tell you that this 10 volt is equal to the VL, also 10 volt. Okay, if you want to draw, can. If you don't want to draw, also can, as long as you know VL is equal to the voltage drop 10 volt here. Doesn't matter, Amin.
Okay. So
Right.
it is not necessary lah, doktor.
Yeah.
Okay, understand. Thank you, doctor.
All right, welcome. As long as you understand, okay, it is regulated and voltage drop there 10 volt, and the voltage drop 10 volt there is equal to the VL because it is in parallel. Okay. All right. I think the end. Okay. So we've done the lecture today. Okay. I thought that I can finish it by 1 hour, but no. You know what? The other class can finish all. I mean, what I've done in the past class and to this class in one class only. Now I've done it in 2.5 class. No, almost 2 class. Okay, it's okay. Doesn't matter. Okay, if we lag behind, then we can do extra class. Are you all okay with that?
Yes,
Okay,
doctor.
as long as you understand, okay, slowly but surely, okay. All right, doesn't matter, okay. Okay, so we've done this. See, a lot of example here. I think I will spare my time for first hour next week for tutorial, okay. First hour next week for tutorial before we start our lecture. Is that okay?
Yes,
Hello?
doctor.
Yes.
Okay. Please respond. No, I'm not angry. Okay, all right. That's great. Okay, so we've done the lecture. Okay, I upload this lecture in the e-learning. Okay, now let's take a look on your. Okay, this is the interesting part. Okay, so now open your multisim now. Do you install your multisim yet?
Yes.
All right, great. Okay, so now I make it smaller here because I have a large screen actually. So I make it smaller. So can you see my multisim
Yes.
and half of my face?
Yes.
Okay. All right. Okay. So open your multisim now. Have you opened? Yeah.
Yes.
Great. Okay, so this is from, okay, let's try one example. So this is from your past class lecture on the example 1. Okay, we want to simulate this now. Okay, all right. Okay, let's take the left side is multisim. Okay, how you take out everything. Okay, when you open, you will get the view something like this, right? I think all of you get the same view like mine, kan?
Hmm.
No.
Yeah, sama.
Sama, great. Okay, so you have in your circuit voltage supply, diode, and also resistor. Okay, I assume that all of you didn't know about multi-stream. Daughter, it is better to be slow and steady. Now? Oh, okay. Just now I said, okay. I thought now. Okay. So place, place. Okay. Yeah, can you see place there? And component. Click component. Okay. So you will get this view. Did you see this view?
Yes.
All right, great. Okay, now I want my power supply. Okay, I take out my diode first. Okay, so this is silicon diode. Okay, usually in any activity that I give you, I will tell you what type of diode you should use. Okay, so these are all the things. Actually, you can scroll down all groups here. Okay, all groups. It has sources, it has basics. So sources mean the voltage supply. AC, as you can see, you have AC current, AC power voltage, AC voltage. Now, you only want a DC voltage, right? Okay, so DC voltage, you go scroll down. Okay, this is DC current, DC power. Okay, so we use DC voltage here, the DC power one. Okay, take this, click OK, and then it will be placed at your circuit here. Can you see that? Okay, just leave it there. Okay, I will change the value later. Okay, okay. Next, you want silicon diode. Okay, go to this group. Okay, click sources. Okay, and then you see diode here. Can you see diode? Hello.
Can.
All right, diodes. Okay. For those who have not, some of you messaged me, said didn't install yet the multi-sim. Doesn't matter. You install later and you watch again this video. Okay. Okay. All right. So I want to use, as you can see here, there is a diode virtual. There is also Zener diode here. Okay. So I want to use diode, silicon diode. Okay, silicon diode. Okay, diode here. Actually, silicon diode, the name is 1N914. Okay, you don't worry about this, okay, student, because I will give you what type of diode you should use. Okay, so for this example, let's together take 1N914. Do you have this model in your multisim?
Yes.
All right, great. Okay, click OK. Click OK and place it here. Okay, done. You have your diode here. Okay, next you have your resistor 2K. Okay, you go to your source, basic. Okay, click group. Okay, and then basic here, basic. Okay, and then find resistor, whatever. I think you take any resistor also can. Okay, later you can change the value actually. Okay, this resistor. Okay. Oh, no. You click here, resistor. Okay. Once you go basic, okay, and then you see bottom here, you go scroll down at the family group, click resistor here. Okay, click resistor. Okay, then there will be a list out of resistor. Let's say I take 1K. Okay, but I want 2K just now, but that's okay. Okay, and then finally your circuit must have ground. Okay, must have ground in your circuit. Okay, so click sources and then you take your ground here, this ground. Okay, this ground. All right. Okay. Now that's it. Okay. Close the select component. Okay. So you have all your component here. Okay. Let's rotate this. Okay. You click this resistor and then you click Control R. It will be rotated. Okay. You click Control R. It will be rotated. Is it rotated at your part? The other side there?
Yes.
Yes. Okay. Okay, now you want to change the value. Okay, the voltage I want here 3 volt. Okay, let's change this 3 volt. Click this 12 volt, double click. Okay, and instead of 12, you change to 3. Okay, click OK. It will be changed to 3. Okay, and then this resistor, you want 2K, but I took 1K, but you can change, double click here, double click this value. Okay, instead of 1K, you change to 2K. Click OK. That's it. Okay, now we want to connect the circuit. Okay, how you do it? Okay, if you go to this point, okay, you will see a dot, black dot here. Just click there and then you connect to your next point here. Until you see a red dot here, you stop. Can you manage to do it on the other side, students? Hello?
Yes, doctor.
Yes,
Yes,
doctor.
and do it
Yes,
for
yes.
do for all. You have experience before with multisim?
For me, no.
I think the other student, do you have experience with multisim?
No, no, no.
Yes. No.
Great,
Fine.
great, great. All right,
We use
great.
Spice before.
It is spice.
I see, I see. Okay, okay. Okay, doesn't matter. Okay, so this is how it looks like. Okay, this is how it looks like. Okay, now here you find that we want to find VR in the circuit, in your circuit here, VR. Oh my God. And also IR. Okay, and also IR. Okay, so VR we use multimeter. Okay, where to find your multimeter? Can you see the right side here? Can you see this right side component here? Okay, find multimeter. Okay, if you click here, this is not multimeter. Wait, I need to make it bigger. Sorry. Okay. Okay, if you go, you go your cursor to this point, you will see there is a multimeter. Can you read that in my view?
Yes.
Multimeter. Next one, function generator. Next one, wattmeter. Next one, oscilloscope. Next one, 4-channel oscilloscope. Okay, so we will be using oscilloscope for the next chapter. For now, we just use multimeter. Okay, click this multimeter and place your multimeter here. Okay, so we want voltage value VR. Okay, so if you want VR, like I told you in the past class, VR at this point. Therefore, VR is across this point to the ground. Okay, means that voltage across 2K. So you take this plus at top of your resistor R1. Okay, and then negative to your other side, ground. Okay, and then you double click this. Okay, double click. Okay, as you can see this. Okay, this multimeter can work as a voltmeter or ammeter. For this particular example, I want to make it as a voltmeter because I want to find the VR. Okay, so you place your voltmeter in parallel with your resistor. Can you see this in parallel? Because it's the same node, right? Okay, so now if you finish this, okay, let's run. Click green play button here. Click run. Okay, so you get 2.398. All of you get 2.398?
Yes, doctor.
All right, great. Okay, so but in your example here, you got 2.3. Okay, why? Because we take exact value 0.7 voltage drop at the silicon diode. But for this model, okay, for this model, the diode voltage drop is a little bit different lah, but almost similar. Okay, almost similar. All right. So this is how you use it. Okay. The voltmeter, the multimeter. Okay, the voltmeter. Okay, now let's see. We want to find the voltage across the diode. How much is actually? So you take another multimeter. Okay, and then you place it here. in parallel because we wonder how much is the voltage here, and then we put it here. All right, and then double click and see. And see how much here. Okay, so play. Run your circuit. So it is about 0.6 volt, okay, not 0.7, okay, but that's okay, doesn't matter, okay, this depends on the diode model that you use. All right, next, okay, next. Okay, so this is the connection of your voltmeter. Okay, if you want to find the voltage, you put your voltmeter in parallel. I think you have the idea with the LT spice. How to find the current across this resistor in LT spice? How did you do it?
Just place a probe,
Just like that,
current probe.
Current probe. Okay. Current probe. All right. Okay. So in this case, like I said, voltage you put in parallel. Okay, the positive probe to this node, the negative probe to this node. But for current, okay, let's put this aside first, like this. Okay, for current, you need to put it in series. Okay, I don't want this because this is quite complicated. Okay, take this out first. Okay, you need to put the your ammeter here. Okay, now you change it to ammeter. Okay, instead of volts, you click A equal to ammeter. Okay, so now it will be function as ammeter. Then you place it in series. Okay, plus to this node, okay, and the other side, the other node is here. That's how you do it to find current. Okay, so here is your, doesn't matter. Let's see whether it works or not. Okay, so this is your connection for ammeter. Okay, ammeter. So let's see. Okay, let's see. So let's run the circuit. Okay, as you can see, you get your current 1.2 milliampere. Okay, in this example, you get 1.15 milliampere because the voltage drop 0.7. Here, the voltage drop 0.6. Okay, that's how you do in multimeter. Okay, in multisim, the connection for voltage is parallel. The connection for current is in series. Okay, are you all clear? Did you try yourself there, over there?
Yeah.
All
Yeah.
right, great. Okay.
Yes, yes.
All right, great. Okay. So if you all try, that would be very good. Okay. So actually, I have I will give you some activity. This is group activity. Okay. So let me show you. Lama. I need to stop this first. Wait. I open too many things and become white. Hang. Yeah. Okay. All right. So actually, I have prepared a very simple circuit lah for you to do some exercise. Okay. So this is computer simulation 1. Okay. So task must be done in a group of 3 or 4 people. Okay. I think I found that there is some 1 or 2 names not here. Section 6, okay. All of you have written your name. But for section 5, there are 3 people who didn't write their name yet in the group. Okay. I will just assign anywhere. Okay. All right. So this is the circuit. All right. So what you should do, you can manually calculate. Okay. Manually calculate. Manually calculate is same like this one. Okay. Like in the slide. And simulation is what I shown you here. Okay. So these are the circuit. Okay, the only 3 simple circuit. Okay, you calculate yourself and then you get the answer. All right. So for circuit 1, okay, given 25 volts. Okay, diode use will update. Use diode 1N914. Okay. And then you calculate, you do the KVL, do the manual calculation, and then you find voltage A, voltage B, voltage C, and voltage D. Okay, how you do it? Okay, so this is okay, and this is circuit 2 and this is circuit 3. So for this, you can see, if you do simulation, you can definitely see the which one is forward bias. Okay, in this case, which one is forward bias? D1 or D2?
Both is forward bias.
Who? Okay.
Right? But
No.
is
No one?
first.
Got
Right?
one.
But the
This is because there is no plus minus here. Of course, we have plus minus here. So plus connected to this plus of diode 1 and plus connected to the negative of diode 2.
two.
Therefore, who will be
D1.
forward? D1 will be
D1
forward
is
bias. All right, great, great. Okay, so where I upload this? Okay, so let me show you. Okay, I have upload the, sorry, hang here. Wait, my computer hang right now. Wait. Okay. Oh my God. Okay. You can use your manual calculation by using hands and then take picture and upload. Okay. But wait, I need to show you something here. Okay, okay. On it. Why become hang? Okay, okay, okay. Sorry, student. It's hang in my part, but yeah. Okay. Okay. So this is your circuit. Okay, so this is your circuit. So what I want you to do is something like this, okay? Where you do your manual calculation to find all voltage and also your simulation. You might want to show something like this, okay? I show you this is what have been done by, okay? So you prove your calculation. Okay, so this is has been simulated. So you prove your calculation like this. Okay, if you calculate VA, you get 25 volt. Okay, VB, you get this value. So in your simulation, you might have to show all these three value. Okay, three value would be the same. Okay. All right. So for this one, I think I have asked you this question in the example here. Is it or no? Or is it different example? I'm not sure. I forgot. Okay. But where did I put this? Actually here. Okay. Have you all ever experienced with Padlet before? Okay. So you do this activity in Padlet. Okay. I will give you the link for Padlet. Okay. First, I have uploaded the question here. Okay. This is note to student. You need to read yourself. And then here are the activity for activity 1. Only 3 circuits, circuit 1, circuit 2, and circuit 3. Okay, what you should do, okay, I have put this, for example, group 051. Okay, the percent monitor. Okay, I have put here, rename the column. So name monitor, also Abdul Rahman. Okay, Abdul Rahman. Okay, Save. Okay. So now you want to give your answer for circuit 1. So you put the title here, answer for circuit 1. Okay. And then maybe you write here is the manual calculation. Okay. All right. So what you do, you discuss in your group, you write in the paper, and then you snap. Okay. You can actually here, you can also okay, upload a file. Okay, it's either you want to upload your PDF file or PNG file, doesn't matter. Okay, doesn't matter. That's how you do it. Okay, and then you do it for another one. Okay, maybe you can straight away say that here is the manual calculation and simulation results, and you upload for both. Okay, the figure for manual calculation as well as simulation. Okay, and then this is the answer for circuit 2. Okay, circuit 2. Okay, so this is for circuit 1. Okay, you can edit, click here, edit post, click here, circuit 1. Okay, I will create all the column for all people, so please do it at your right column. Okay, and write your name as well, and so on for circuit 3. Okay, I think that's all. You can do it by today or during the weekend. Okay, so this is just the activity, simulation activity within you and your group. Okay, for example, group 5. So this is the member. Okay, for example, section 5, group 2. Okay, Yip Wen Chuan, Li Peng Ang, Alex, and Liu Kangjing. So you can discuss between you. Okay, you can have your own waybacks and then discuss, and then or you discuss through WhatsApp and then get the final answer and upload your answer here. Okay, I will add the column later. Please write down at the right column. Okay, all right, that's all. Student, are you all there?
Yeah, the
Yes, Doctor.
All right, all right,
Yes,
all right.
doctor.
Okay, all right. Oh, so Nashra have class now. Okay, you may leave now. Okay, I was about to end my class now. All right, I
Okay,
think
thank
that's
you, doctor.
it. I will give the Padlet link later. Okay, after I update everything. I hope everything's clear today. You have learned very much clear about today lecture and also the assignment and the multi-sim as well. Okay, all right. Anything else? Attendance. Yeah, one more time. I will show the attendance. Yes. Yes. Who said just now? What? Hello? Right. Here is the attendance. Okay. All right, student. Take care, and I see you next week. I will give you the link for Padlet, and I hope you do your activity with your friend. It won't take so much time. Very easy, the simulation. Okay. All right. Bye all.
Bye, Doctor.
Alright, thank you, Doctor.
Bye. All
Thank you,
right.
Doctor.
Welcome. Take care all. Have a nice weekend. Oh no, one more day tomorrow. Okay, all. Welcome, welcome, welcome. All right, welcome.
Doctor,
Yes, yes.
about the PIV, how to explain?
About the PIV. So PIV is the peak inverse voltage. It is actually voltage at both. Okay, so when you have for example, one side, when you have positive cycle, there will be a diode forward bias, but there will be also diode reverse bias, right? So that reverse bias diode, it has peak inverse voltage, means the maximum voltage that could be occurred during the reverse bias. That is peak inverse voltage. So when you calculate peak inverse voltage, it is actually voltage across reverse bias diode. Okay.
Okay. Thank you, Doctor.
All right. Welcome. Okay. All right. Bye all. I will close there.